All right, section 8.2, the law of cosines. Back in section 8.1, we talked about 5 different situations, 5 different cases that would come up in solving of triangles, depending upon the lengths of sides or measures of angles that you knew. Now, in that section, we dealt with 3 cases. We dealt with the AAS case and the ASA case, those 2 cases where we knew 2 angles and a side, which were essentially the same because once we found that third angle, finding the other 2 sides proceeded the same in both cases. We then had that SSA case that we call that the ambiguous case, where we knew 2 sides and a non-included angle. Right? And that was the one that led us to those three different possible solutions where we could have 0, 1, or 2 triangles, just depending upon the information that we had. So we had issues there that we dealt with. We had 2 other cases, though, that we mentioned. We had the SAS case, where I know 2 sides and the included angle, or the angle between those 2 sides, and the SSS case, where we knew 3 sides and no angles. And in those 2 situations, we couldn't use law of sines because law of sines requires that we know an angle and a side opposite each other. And in those 2 cases, we don't. So that's what leads us to this law of cosines to deal with those 2 situations, or at least initially, to help us find the first piece of information. Now, law of cosines, giving you this a little more straightforward. These are just going to be more formulas that we're going to have to memorize in terms of, first of all, what information do I know? Which formula do I have to use? And that's what I mentioned before. You have to now recognize, am I going to use law of sines or am I going to use law of cosines? And it's all dictated by what information you have, or the relationship or the orientation between the sides and or angles that you know. So the law of cosines tells us this. I can find the length of a side if I know the 2 other sides and the angle between those 2 sides by taking the sum of the squares of those 2 sides minus twice their product times the cosine of the angle included between those 2 sides. Right? So for example, if I know the length of side B, I know the length of side C, and I know the measure of this angle A. Right? So I can start by finding the length of side A using this law of cosines. Now, once you have the length of side A, now you know a side and an angle that are opposite each other. You could then proceed to finding either angle B or angle C using the law of sines. Or you could use law of cosines again. Either way. And I'll show you an example. I'll do it both ways. But ultimately, that is going to be your choice as far as which way you care to proceed once you find that first piece of information. Now, I also want you to notice something else with this law of cosines. And let's maybe look at the third one. If you knock this out, that's a squared plus b squared equals c squared. Most of us, that's how we remember Pythagorean's theorem, right, that we use for finding the lengths of sides of a right triangle. So the sum of the squares of the sides equals the square of the hypotenuse. But since this is not a right triangle, right, we have more to it than just that. So in the case of these oblique or non-right triangles, it is Pythagorean's theorem, but then there's more to it, this other piece tacked on. Now also recognize this, though. If the angle is a right angle, this angle C was our 90-degree angle, what's the cosine of 90 degrees? Cosine of 90 degrees is 0. So that would actually make this 0, and you're right back to Pythagorean's theorem. But again, that's because angle C was a right angle. Okay? So, I mean, the law of cosines works, whether it's a right triangle or not. It's just with right triangles, we don't need that back end of it because the right angle has a cosine of 0. Okay? But bottom line is, if I know 2 sides and the included angle, I can plug that information in to our law of cosines, and I can start by finding the length of that third side. From there, I could use either law of sines or law of cosines to find one of my remaining angles. Now, the second situation, or the other case where this is used, is in that SSS case, where we know 3 sides and no angles. Now, you could use this same formula. If I knew, say, the lengths of sides A, B, and C. I could plug those into this formula. I could plug in A, I could plug in B, I could plug in C. And again, there's B and C. And the only unknown is angle A. So I could then solve that equation for cosine A and then find angle A. Right? Equivalently, whichever one we use, depending upon, which or how our angles and sides are labeled. We keep saying with that it's all arbitrary in terms of how you label your angles and your sides. So it's more about the orientation in the information. Do I know two sides and an angle opposite included, or do I know three sides and no angles? Then this law of cosines comes into play. Now, these equations are just a rewriting of those previous equations, solving it for cosine A, cosine B, cosine C. So, like we've done before with formulas or identities, that kind of thing, I have the basic formula, a squared equals b squared plus c squared minus 2bc cosine A. I can plug in the information I have, solve for the missing piece. In the case that you're looking for the angle, you could alternatively just memorize this formula. But it's the same formula, just rewritten. So when I do my examples, I'm going to use these when I'm looking for the angle, just because, again, it's a rewriting of this one. Saves us a little bit of time instead of having to solve for cosine. We already have that done. But that's, again, a case where, how much you want to memorize versus just use the basic formula and solve it for the missing piece. Right? So that's either way, again, you care to do that. I don't care, it's up to you. But that's our law of cosines. Right? After that, it's just a matter of using the formulas. Right? So just like we did in the previous section. Now again, you ultimately come test time, right, you're going to have to recognize when to use which law. Right? We said the easiest way to recognize, or do I use law of sines or law of cosines? Do I know a side and an angle opposite each other? If I do, I can use law of sines. I can set that ratio up, and then my other ratio depending upon what other information I know. If I don't know a side and angle opposite each other, then law of cosines is going to be used. Now, whether you find first the third side or one of your angles, again, that will just depend on which information you have. So our first example is going to be an example of the SAS case. I know two sides, side A and side C, and I know the angle between those two sides. Now, you can always recognize that because, again, if I knew an angle and side opposite each other, I would have either angle A or angle C there. The fact that I have angle B, that would be the angle that lies between sides A and side C. So there's our law of cosines. So let's start with that guy. And so the first thing that I'm going to find is that third side. Now, how you choose to write this equation. Again, you do enough of these, you do a couple, you start seeing some shortcuts. All right, and maybe you can streamline the process a little bit if you recognize how these calculations play out. But you can always start with the basics and then work the equation or rewrite the equation as needed. But if I'm looking for side B, so I'm just going to start off with the generic formula, law of cosines, that says b squared would be equal to the sum of the squares of the other two sides minus twice their product times the cosine, not B, or not A rather, B, times the cosine of that included angle. Right? Or you could say directly that B would be equal to the square root of all of that, right? So B would be a squared plus c squared minus 2ac cosine of B. So that's just a matter of how you care to do it. I'm going to start off usually with that generic formula, and then I rewrite it this way. All right, but that's what I'm going to plug into my calculator. That way I only have to do it or do one calculation. So in this case, that would mean that I'm equal to the square root. A is 12 and C is 15. So I've got 12 squared plus 15 squared minus twice their product and the cosine of our included angle. And that would give you B approximately equal to 25. I'm going to go ahead and round that to the whole number because the other two sides are given as whole numbers, so I'll go ahead and do that. But that is the length of side B. Now, once you have the length of side B, you now have options as far as how you find or want to find the measures of the two remaining angles. We're missing angle A, we're missing angle C. Now I know an angle and side opposite each other, right? I know side B and angle B. I can use law of sines here if I wished. And I can set up law of sines to maybe find angle A. I'll pick that one, I'll do that first. Or you could use law of cosines. I'm going to do it both ways just to show you. Right? But then going forward after that, again, it's just up to you. It's your preference as far as which way you prefer to do it. So let's first, I'm going to find A. Let's do it using the law of sines, right? Since now we know a side and angle opposite each other, let's go ahead and set up our ratio. I'm looking for angle A, so I'm going to go sine A over side A, which is 12. And we can set that equal now to sine of B, which was in the original problem, over B that we just found, or at least its approximation. So then solve that for sine A. And this is exactly what we did in that last section. So I've got sine A equal to 12 times the sine of 133 over 25. And then, like we said, you could either approximate that value and then do your inverse sine, or you could take the inverse sine of that value. And again, that's just all a matter of how you prefer to do it. I'm going to go ahead and approximate that sine value. Sine A is approximately 0.3510, actually it would round if you go 4 decimal places. So 0.351 or 0.3510, either way. And then we'll have A equal to the inverse sine of that value. .351 or 0.3510. And that would give you the measure of angle A at approximately 21 degrees. But remember, here was the drawback. Here was the issue that we had when we were finding the angle. When you take that inverse sine, remember there's always going to be two angles that have that function value. It's a positive sine value. That's positive in Q1 and Q2. Here's our Q1 angle. Back when we did our law of sines, we also had to take into account the fact that there was a second angle. And then we had to check to see if we had room in our triangle for that angle. Now, you still have to take that into consideration here, but here's the good part of it. The law of cosines, there is no ambiguous case. The law of cosines, there's only possibly one triangle that can be formed. So unlike the law of sines where we had to deal with possibly two triangles coming out of this, the law of cosines, that's not going to be the case. But normally yes, we would have to deal with or take that second angle into account. So I'm just going to, as a reminder, we would say that possibly that angle A could be equal to 180 minus 21. And that would give us a possible angle of 159 degrees. But, we said you'd have to check the measure of that angle. Notice in our original information, our triangle already has a 133 degree angle. There's no way I can have an angle of 159 degrees in that triangle. All right, that's way too big, not a possible angle. We also have made the observation before that with a triangle that has an obtuse angle, there's only one possible triangle that could be formed there. Right? You can't have two obtuse angles in a triangle. Right? So yeah, you still have that in to consider, but it really becomes a non-issue because with this law of cosines, there is no ambiguity. There is no ambiguous case. Right? But just kind of as reference, don't forget that when you are dealing with law of sines, you always have to check to see if that second triangle is a possibility. Now, once you find that angle A, you've got two angles. You can find your third angle, angle C. By subtracting the two angles that we know from 180 degrees. Right, so we had angle B, 133 degrees, and our angle A of 21 degrees. And that would leave us with angle C of 26 degrees. Now, I said you could do this two different ways. So that's finding angle A using the law of sines. We could also do this using law of cosines. Now, if I use the law of cosines, then I'm going to use one of those formulas that we had on our slide. Since I'm looking for angle A, I'm going to say that the cosine of A can be found by adding b squared plus c squared, subtracting a squared, and dividing by 2bc. Okay. Now again, that's the a squared plus b, or a squared equals b squared plus c squared minus 2bc cosine A, just rewritten. I solved it for cosine A. I'll plug in my information and I get the cosine of angle A. So plugging in what we have, we've got now all three sides because I know the length of side B now, or at least we have an approximation for it. So we have our A and C 12 and 15, B is 25. So I've got 25 squared plus 15 squared minus 12 squared all over 2bc, 2 times 25 times 15. And that will give you approximately 0.9413. Now that's our cosine value for angle A. So then A would be equal to the inverse cosine of that value. Now, when you round this to the nearest whole number, this is going to give you approximately 20 degrees. All right. Now notice that's different from what we got above. When we did it using law of sines, we got approximately 21 degrees. Doing law of cosines, we got approximately 20 degrees. That's what I keep harping on about approximating with approximations, right? Because remember, we had an approximation on the length of side B of 25, and then we used that in these calculations. And so then when you're using an approximation, and again, doing an approximation, you're not going to get exactly the same value each time. All right. So there is some variation here. Now, this is built into MyMathLab. Don't sweat it on MyMathLab in terms of, well, do I have to do it a certain way? They have a certain margin of error built into the answers for these solving of triangles because of this. Because depending upon which method you prefer to use or care to use, which law you use, and depending upon how much approximations or how the approximations are done, you can get some variations in your final answers. Right? So that is taken into consideration. Now, if you're too far off, yeah, it'll mark it wrong. But there is a reasonable allowance for approximation and all of that. So, yeah, so you can still do it either way you want, but just be aware that you do get different answers sometimes doing it different ways, right? And that's just due to the whole the approximation stuff that's being done. So that would give me angle A of 20 degrees, and then of course we'd get a different angle for angle C as well. So then angle C now would be 180 minus the 133 for angle B, but now minus 20 degrees that we had for angle A, and that would give us angle C of 27 degrees in this case. All right. So just be aware of that. If you do it differently, you can get a little different answer because of all the approximation stuff. Okay? Here's number 2. This is an SSS case. This is the case where we know all 3 sides and no angles. Right? So we have no choice here but to start by finding one of our angles. My recommendation is to start with the largest angle. I mean, it really doesn't matter. You can start with whichever one you wish. I always prefer to start with the largest angle. That way, once you find that first angle, if you choose to do law of sines to find your second angle, it takes out a lot of that ambiguity, a lot of that possibility for, or having to deal with all those different possible angles that can come out of the law of sines. So that's my recommendation. Yeah, again, it doesn't matter. Right, so I'm going to start by finding angle C. I know angle C is the largest angle because it's opposite the largest side. Right? The longest side is side C, so the largest angle would be angle C. So I'm going to start there. And let's find angle C using law of cosines. So I'll start with this equation, and that the cosine of my angle is equal to the sum of the squares of those 2 sides minus the square of the side opposite my angle divided by 280. All right, and as we always say with any of these formulas, whatever works to help you memorize that. All right, so again, we're just going to plug in our information. All right, so I've got a squared plus b squared. I've got 16 squared plus 20 squared minus c squared over 2ab. And that will give you approximately, well, actually this one comes out evenly, negative 0.575. You don't get that often, in that you do get an exact value. But that is our cosine of C. So then I'll say that C is equal to the inverse cosine of that. Now again, if you prefer, you could do directly the inverse cosine of all of that stuff, right? And just do it all in one calculation. So that again is up to you. I mean, it really doesn't matter in this case. We talked about in that last section when we're doing inverse sine, because of that whole ambiguous case thing, I found it better to find this first and then deal with this. But here, since you don't have that issue, finding the inverse cosine of all of that, if you want to just type all that in as one calculation, that'll work fine as well. But this gives us an approximate angle of 125 degrees. And that would be the measure of angle C, right? Now, like we said before, once you find this first piece of information, once I find, in this case, angle C, now I have an angle and side opposite each other. I have angle C and side C. So I can proceed to finding either angle A or angle B using law of sines, or I could use law of cosines. I'm going to go ahead and use law of cosines this time. And I'm going to find B. No particular reason. B is the next largest angle because it's opposite the next largest side. Doesn't matter. Pick your poison. So let's go with the cosine of B. Angle B. Cosine of B being equal to the sum of the squares of A and C minus the square of b over twice the product of those two sides. Plug all that in. So I've got a squared 16, c squared is 32 squared, minus b squared over 2ac. And that gives you an approximate value of 0.8594. So then angle B would be equal to the inverse cosine of that measure, of that value. And that'll give you approximately 31 degrees. And that is the measure of angle B. Now, once I have angle B, finding angle A, so 180 minus the two angles that we just found, right? Angle C, and then minus angle B. And that leaves us with 24 degrees for angle A. Okay. Now again, you could have chosen to find angle B using law of sines if you prefer. Okay. Your choice. Either way works. All right, so those are the two generic cases, right? That's our SAS and SSS case. As usual, here's the fun stuff. Applications. I know you love them. So, diagram, right? As I always say with these, can I construct a diagram to model the situation? Once we have the diagram, then we're just back to solving the triangle. So for this first one, we got a circus high wire act that walks up an approach wire to reach a high wire. The approach wire is 122 feet long and is anchored so that it forms an angle of 35 degrees with the ground. If the wire is anchored 30 feet farther back, how much farther will they have to walk up that approach wire, and what will the new approach wire be? So here's our information. We started off with walking up an approach wire that was 122 feet long to reach the high wire. We were told that it was anchored so that it formed a 35-degree angle with the ground. We then said, okay, if they took the anchor and moved it back 30 feet farther back, we now have a new approach wire. How long is the new approach wire, right? How much farther are they going to have to walk up the approach wire to get to the high wire? And what is this new approach angle going to be? All right. Okay. Well, information. Since I'm looking for this, and I'm looking for this, here's our triangle that we're interested in. And I'm looking for a side and an angle of that triangle. Now, we already know two sides of that triangle, right? We know the 30-foot side, we know the 122-foot side. So in other words, this is basically, right, the triangle that we're finding or solving. Like I tell you, you may find it helpful to just resketch or sketch yourself a triangle that's outside of the original picture to get out all that cumbersome stuff. We know this is 30. We know this is 122. I bet we can find this. Because right here, we've got 180 degrees. And if I subtract that from 180 degrees, that 35-degree angle, that'll give me the measure of that angle within my triangle. Okay. So let's label our triangle. Now again, the labeling here is purely arbitrary. Use whatever letters you want, wherever you want to use them. I'm just going to call this angle A. I'm going to call this angle B. I'm going to call this angle C. So we can find angle C in our triangle by subtracting that 35 degrees from 180. And that'll leave us with what, 145 degrees. So there is the measure of angle C. Now once I have that, we're back to business as usual. All right. Now we're just solving that triangle where we are looking for the length of this side, side C, and we're looking for the measure of this angle, angle A. Now again, recognition here, what do I know? I know two sides and the included angle. That is law of cosines. So let's first start by finding the side opposite the angle that we know. So that's our straightforward law of cosines, and that's c squared, the third side, is equal to the sum of the squares of the first two sides minus twice their product and the cosine of that included angle. Keep putting my angle measure, cosine of C. Or again, we said we'll just take the square root of that. So how about then C equal to the square root of all of this? A squared plus B squared minus 2AB cosine of C. And we'll just plug everything in. Let me just do it down here. So I've got C equal to square root of A squared plus B squared. A would be here, opposite angle A. B would be here, opposite angle B. Right? So I'll go 122 squared plus 30 squared minus twice their product and the cosine of our angle, 145. Okay. And that will give you approximately 148 to the nearest whole number. And that would be 148 feet. Remember, that is the length of the wire. And so that's the length of side C of our triangle. But in the context of our application, it was the length of our approach wire, so 148 feet. So we could say then that how much farther, right, they had to walk up the approach wire. So the original was 122, the new one is 148. So that would give me what, 26 feet farther. Okay. Now we're also asked to find the approach angle. Right, so I'm looking for angle A. Right, now again, you have your choice here as far as do you use law of cosines or law of sines. Doesn't matter. I now know a side and angle opposite each other. I did the last one using law of cosines. I will do law of sines this time. All right. But bottom line is we need to find angle A. Now that we know the length of side C and the measure of angle C, I could set up my law of sines with A sine A and C sine C. And since I am looking for angle A, I'm going to put my angle on top. Sine A over A, which was, what, 122. And I can use C and sine C now that I know both of those. So sine of C over the length of side C, or at least that approximation that we just got. So then we'll solve that for sine A. And now we're back to business as usual. And that will give you an approximate sine value of 0.4728. So that angle A then would be equal to the inverse sine of 0.4728, which gives us approximately 28 degrees. And that is angle A, which is our new approach angle that we were asked to find. Okay. But again, you have your choice there. Log cosines, log sines, either one. That looks interesting. Batter in a baseball game. Drops a bunt down the first baseline. The ball rolls 34 feet at an angle of 25 degrees with the base path. The pitcher's mound is 60.5 feet from home plate. How far must the pitcher travel to pick up the ball? So that's our diagram. I've got home plate. We've got the first baseline. The batter drops a bunt down the first baseline. That makes an angle of 25 degrees with the base path. We're given that the distance from home plate to the pitcher's mound is 60.5 feet. And we're asked to find how far does the pitcher have to run to pick up the ball. So I have everything kind of labeled here according to what it represents, right? So H is home plate, F is first base, P is the pitcher's mound, B is where the ball ends up. Now I've also drawn in third base as well. There's a reason for that here, because a baseball diamond is a square. That's important information here because that tells me that this angle H is a 90-degree angle, which means that the angle then between the pitcher's mound and the first baseline would have to be a 45-degree angle, right? Because this angle, let me do this, right? This angle would have to be 45 degrees because it's half of this guy. Right. Now that's important because that'll help us find that angle H that's in our little triangle. Right, so that's actually key information that we need to know to help us find the values or the information that we need to solve our triangle. So here's the basic makeup of here's our triangle that we're looking at. Here's home plate to the pitcher's mound. There's out to the ball. And there's from the ball again to the pitcher's mound. So that is our B. There's home plate. Here's P. Right. Now, we know this side is 60.5 feet. We are looking for this side. We also know what, I'm missing something here. The ball rolled a distance of 34 feet. So that would be the distance traveled by the ball of 34 feet. Now, given the information that we just described over here, I think we could find the measure of angle H in our triangle, because we said this angle has to be 45 degrees, which means angle H would have to be 20. If we subtract out, I'm gonna squeeze this in here if it kills me. There we go. We have to subtract out the 25 that we know. Leaves us with an angle of 20 degrees here. Okay. Now again, law of cosine versus law of sines. What do I know? I know two sides and an included angle. Right? Our main observation is, like we say, I don't know an angle and a sine opposite each other. So I cannot use law of sines. I'm going to have to use law of cosines. So I'm going to call this side H, the one that we're missing, since it's opposite angle H. And using law of cosines, I've got H squared equal to the sum of the squares of the other two sides. And we can call this side P, it's opposite the pitcher's mound. We'll call this side B, opposite the ball. So how about P squared plus B squared? Minus 2PB, and the cosine of that included angle. Right? Like I said, it's all arbitrary in terms of how you label these things. It's all about the orientation. That's the main thing. So label it however you wish, call them whatever you want to call them. You just got to keep track of which angle is which side is which, who's opposite who, that kind of thing. So again, here I can take the square root. So I have H equal to the square root of all of that, P squared plus B squared minus 2PB, cosine of H, and then we'll plug in our information. So P squared, 34. Plus B squared minus twice their product. H was what? 20 degrees. It's the one we found up there. And plugging all that in gives us approximately, to the nearest whole number, 31 feet. All right. Now again, that's the length of side H of our triangle, which ultimately was how far the pitcher had to run to get the ball. All right. So that would be 31 feet. Okay. That's it for that section. See you in section 8.3.